This is the pre-lab lecture for lab number 7, CMOS gate circuits. So in this lab we're going to be using some Boolean algebra, and just to make sure we're all on the same page with notation, and the AND algebraic function will be represented by a star or by a plus, not by an overline. And there are a couple of algebraic rules that you need to do these derivations. The first is that not A is the same thing as A. So if A is 0, then you invert it, you get a 1, you invert it again, you get back to 0. So that's a useful and interesting fact. And the second is De Morgan's law, and in the handout I described De Morgan's law a little bit better. One way to think about De Morgan's law algebraically or graphically is if you break the bar in the middle, you switch the OR to an AND, or you break the bar in the middle and you switch the AND to an OR. So these two are equivalent, and you can prove that to yourself just by doing a little truth table with ones and zeros. So, and I'll show you a truth table here in a few minutes. So that's the basics of Boolean algebra that you'll need for this lab. So what we're doing in CMOS circuits is you've got a pull-up network and a pull-down network, and you've seen this before. The simplest pull-up network is a single transistor, a single p-channel transistor. The simplest pull-down network is a single n-channel transistor. And if you have those, you end up with an inverter. So you've seen that before. What we're going to do in general is we're going to make a pull-up network that has multiple inputs that activates whenever Y should be high. And then we'll make a pull-down network that, again, has the same set of inputs, but it activates whenever Y should be low. These are called complementary because these are designed so that one and only one is ever on at a time. So that's what the mutually exclusive means, is that the situations that cause the PUN to be active are exactly the opposite from those that cause the PDN to be active. So let's look at a couple example pull-down networks. So this is an OR gate, or the pull-down network for an OR gate. So instead of thinking about Y for a pull-down network, we want to ask when should this be active? In other words, when should Y be low? So we write an equation for Y bar. So Y should be low when A is high or when B is high. So if we look, this is a n-channel device, so when A is high, VGS is 5 volts and QA is in the triode region. Same thing with B. When B is high, QB is in the triode region. So if A is high, you have a low impedance path or a small resistor between Y and ground. So Y is a 0, or B, or both. So two transistors in parallel lead to an OR. Same thing with a NAND here. Now we're looking at when is Y low? Well, Y low for an NAND, Y is low when A is B and when high is B. When B is high, sorry. So let's look at the circuit that goes with that. When B is high, then VGS is 5 volts and QB is in triode region. So then VGS for QA is slightly less than 5, but it's still should be above the threshold voltage. So QA is also active. So when A is high and B is high is the only situation where I have two transistors in triode region between the output and ground. So that causes this to be low. All other combinations, one or the other or both, are in the cutoff region, and so Y is not pulled down. Now we'll have to look up the pull-up network to see what happens to it, but we know it's not pulled down. And you don't have to do this with the basic ones. There's a custom gate here that we're looking at. So here, Y should be low when A is high or when B is high and C is low. So this looks the same. So the OR leads to two parallel branches, and then the AND leads to a series branch. And the other thing to note is that we're feeding this gate with not C. You saw last week how we make an inverter. So we'll actually use an N-channel and a P-channel device to make an inverter off to the side, and we'll feed the output of that inverter to this gate here. So anytime you have an inverted input, you just design a separate inverter for that. So those are pull-down networks, and those are 3 examples. They're described in Sedra and Smith, and they're described in the handout. The pull-up networks are a little bit different. The pull-up networks now, we're looking at what causes Y to be high. And these are p-channel devices, so QA is in triode region when VGS is -5. So when A is low. So what you have to do is you have to come up with an equation for Y in terms of ands and ors of your inputs. So for a NOR gate, then Y is just A or B with the whole thing knotted. And that's equivalent to, using De Morgan's law, A bar and B bar. So again, and is 2 series things. So Y is active when A is low. That causes QA to be in triode region, and when B is low, which causes QB to be in triode region. So here we have the inverted, or the complement of our inputs. So that's the tricky part about pull-up networks is even though I write A here, A bar shows up in the equation. Similarly for a NAND gate then, I take the original equation and I break it up using De Morgan's law, so I have A bar or B bar, and OR leads to parallel paths, so Y is high if A is low, or if B is low, or both. Our custom gate then, you have to use a little more Boolean algebra on. So we start off with our original equation, and we have an equation for Y, and then we use De Morgan's law on this plus to make it a star. So we have A bar or this second term. Then we use De Morgan again to break apart B and C bar, and so that gives us B bar or C bar bar. Then we use involution to realize that C bar bar is the same thing as C. So this is our equation that we implement. So Y, which is here, is 1 when A is low and when either B is low or not C is low. So notice that we have not C here. Since that's a p-channel device, you get an extra inversion there. So if you go back and compare the pull-down networks to pull-up networks, the equations are exactly the opposite of each other. So here we have Y bar is A or B C bar, and here we have Y is not A and B bar or C. So this is the opposite of the previous one. And so either the pull-up network or the pull-down network will be active, but not both. So let's look at the practical details of doing these in lab. We ask you to set up your protoboard like this, and this is just to make your life easy for the next couple of weeks. So the input area is going to contain all the switch circuits. So for each of these, and if you use this, you'll have 4 switches in a single dual inline package. So you would have 4 switches and 4 resistors, all independent. And on the switch side of the resistor is where you're going to peel the input off. So this lets you generate a 1 or a 0 using a switch. You don't have to be moving the wires around like you did last week. So in the switch area, you'll have 4 independent switches here. And then in the output area, one note I forgot to mention is that these switches are marked on. On for a switch means it's closed. If you look at this circuit up here, closed means 0 volts. So when the switch is on, V is low. When the switch is off, V is high. So that's kind of opposite from what you might think if you weren't carefully considering the switch. So on is actually low. So keep that in mind. Then let's talk about the output area next. This is the circuit that we're going to use for an output circuit. And the reason that we're doing it this way, so we've got an inverter here. So you're going to be using a 7404 like we did last week. It has 6 of these on there. So you, in theory, have 6 independent inverters in your output area, each of which can drive 1 LED. You'll only need 2 or 3 at the most. but you certainly only need one 7404 out here. If we look at the data sheet for the 7404, you see that when the output is high, it can only source 400 microamps, but when the output is low, it can sink 16 milliamps. The LEDs we're using are designed to be used at 20 milliamps. So if we just hooked them up in the most obvious way, which is we connected up the anode to the output of our test and ran it to ground, this thing would never light up our LED. So we actually have to flip the LED around and put the anode up here at next to the resistor and the cathode down at the output. So what this does is it lights up when the output is low. Since I have an inverter here, then it lights up when V is high. So if you consider the resistor, the LED, and the inverter as a package and put them all here in the output area, then you'll have a circuit which lights up when V is high and doesn't light up when V is low. So that's usually what we want to do. And that's just because of the particular characteristics, the current characteristics of our TTL chips that we're going to be using. And the same thing is true of CMOS as well, so it doesn't really matter. So we flip around the LED, we've put it backwards, and these inverters are here in the output area. And that's separate from any inverters you decide to use in your test area. So we've got switches on the left column, outputs on the right column, and in the middle is what you're going to be playing with. So you're going to build several different test areas in the middle. One thing to point out is that since the first couple of chips you see tend to have this layout where 1 and 2 are inputs and 3 is an output, students tend to assume that all of them are that way, and that's not the case. You actually have to look up the pinout for each individual kind of chip. So for example, if we have NOR gates, 2 and 3 are inputs and 1 is an output. So if you hook pin 1, if you hook pin 3 up to an LED, you're just going to get garbage. So always check your data sheets to see what your pinouts are. So any Boolean function can be represented either with an equation or with a circuit or with a truth table, and they're all completely equivalent. And one thing about truth tables is you want to always do them in the same order. So that makes it real easy to compare. So this is what we call binary count order. So if I consider A and B as a number, this is 0, 1, 2, 3. So 0, 1 is binary for 2, and 1, 0 is binary, or sorry, 0, 1 is binary for 1, 1, 0 is binary for 2, and then 1, 1 is binary for 3. So these are just truth tables in the correct order for 2, 3, and 4 input functions. So anytime you do a truth table, you want to do them in the same order, and that makes it easier to compare and to work with it. So what's the experimental procedure for this week? Well, first you're going to build a standard gate, a NAND gate. And I recommend you first build the pull-up network and then just use a resistor for the pull-down. So the pull-up network is what you're working on testing. Once you run that through the full truth table and you verify that everything's working properly, then you're going to separately wire the pull-down network out of transistors with a pull-up resistor. Once you've gotten each of these, so these two should have identical truth tables for them. And then once you get both of those done, you're going to get rid of your pull-up and your pull-down resistor and connect up the standard CMOS circuit, which is a pull-up network connected to a pull-down network. So all three of these should exactly match your predicted functions that you got in Prelab. Then you're going to come up with your own custom gate. So you come up with an equation, and no, it can't be a NAND gate, it can't be a NOR gate, you got to do something different. And come up with something with realizable inputs and outputs. So you have to be able to imagine for the inputs making a sensor or making a circuit that could detect that. So the example I use in the handout is you can imagine making a circuit that detected whether there was a key in the switch. That's not hard. But making a circuit that determined whether the Broncos won last night, that's not going to happen. So make a realizable input. And same thing with the outputs. An output that turns a light on or that makes a siren go off, that's just fine. An output that, I can't even think of a non-realizable output right now. So you want to make sure that you can make not that you have to make it, but that you could make a circuit that would do what you say. So we want these to be kind of more real world gates. And you're going to follow the same procedure for your custom gate that you did for the NAND. So you're going to first do the pull up with a pull down resistor, and then the pull down with a pull up resistor. Then you're going to get rid of the resistors and test them all. Again, all three should be identical in terms of highs and lows. We're no longer worried really about the voltages of the inputs and the outputs. We're really worried about whether they're high or low. So I will see you in the lab.